because this stuff can be really tricky, I am boring and redundant. So you're just going to keep getting the same story from me essentially in terms of understanding these pressure cells and movements. So again, Coriolis effect is going to create that deflection in the northern and southern hemisphere, clockwise and counterclockwise, and it's going to then after those high pressure cells and those low pressure cells to spin. So they're spinning and lifting and spinning and falling, creating those cyclones and those anticyclones. So nice global distribution model of the circulation of the atmosphere right here. And what's nice about this diagram is it gives you the ITCZ, it gives you the Ferrel cells, the Hadley cells, the polar cells. What I want to draw to your attention is a couple of more terms here that don't show up elsewhere that are interesting. In the ITCZ, we have something called an equatorial doldrum. And if you use the word doldrum colloquially, you often think, oh, I'm in the doldrums. I'm kind of like, I don't want to move. I'm kind of, not feeling so hot. Doldrums is exactly that. Right at that low pressure cell, there is no movement. In the center of high pressure cells, in the very center of low pressure cells, there is static energy. There's no movement. And that becomes a problem if you are a mariner that is relying on wind, because you need wind in your sails. So the doldrums become a problem. You don't want to get caught in them because you're not going to move across the ocean with those doldrums. With 30 degrees latitude, where the high pressure cells are, these are often termed the horse latitudes, and they're termed the horse latitudes for the same reason that the doldrums are called the doldrums, is because there's no movement of energy. Unfortunately, it's a little more nefarious, because if you were a mariner and you were coming out of Spain or France or Britain, and you're coming across the continent and you're carrying horses with you, and you find that you have left Spain too late in the year and you're in the middle of a high pressure cell, you're not moving across the ocean. You have to figure out how to get across the ocean, and in order to maximize your ability to move, you've got to lighten your load, because if a little bit of wind comes up, you want to travel as far as you can with that wind. You can't give up your water. You can't give up some of your humans. You can't give up your food. So the only thing to give up were your horses. So they unfortunately would throw the horses overboard at these latitudes. And so the humans wouldn't die. So rotten story, but that's how the horse latitudes got their name. At 60 degrees latitude, we have the polar front. And the polar front is that margin where we get a polar jet stream. And it's the polar jet stream and the polar front that you and I look for in the wintertime. It marks when we get extended cold weather, is at the polar front. This polar cell, which is bringing cold air from the Arctic, is going to move and lock in and circulate around back and forth. So once that polar front crosses to the south below us in Youngstown, or below us in Pittsburgh, or wherever you happen to live, then you're going to be in stable air, but it's going to be stable and cold. And remember, where you have lift, it's going to be unstable. So in the summertime, when all of the cells are moving northward, when the polar front moves to our north, the energy is going to be stable, but it'll be stable and warm. So when movement is occurring, it's occurring during the spring and the fall, and that air mass, which has generated a cloud mass, is going to precipitate out rain or snow. So when we think about when we get the most amount of precipitation, it's during those spring and fall seasons, when the Hadley cell and the polar cell and the Ferrel cell are moving back and forth, and the polar front, where this cloud mass is pushing all of that lifted energy around and pulling that moisture back out of the sky onto us. So that covers that slide. So again, just a really nice diagram to help exemplify what's happening with these polar cells and these subtropical highs. When we've got a subtropical high, and I like the fact that this is using Africa, but it becomes a little hard to imagine North America. What ends up happening is that this polar high in the summertime moves northward. So in the summertime, we often get a loss of moisture. There's much less rain happening than in the springtime. We might get some convective rain cells, and we'll talk about convective heating and convective clouds a little bit later. But the multiple days of rain and the steady days of rain don't exist anymore, and we end up in a seasonal drought in the summertime because we're under a high pressure cell, which results in loss of rain and then a little bit of desiccation. So again, where the intertropical inversion zone is broad, that moisture, which is being carried by this cloud, is going to move back and forth across here. Now, we don't get a lot of temperature variability at the equatorial region because the volume of sunlight every day doesn't change too much. But the thing that does change is the amount of moisture. So it's in the intertropical convergence zone that we get wet seasons and dry seasons. And closest to the equator, we have the largest volume of rain. It's happening twice a year here. Up here, it only happens once a year when it comes to 23.5 degrees north. And when it comes around to 23.5 degrees south, it only happens once a year. So there is more drought here, less drought here, more drought here. But this is going to bring rainy seasons and dry seasons. And because if we watch, if this is March, we go March, April, May, June, then June, July, August, September. So all these places in here got 2 periods of rain. Likewise in the southern hemisphere. June, July, August, September, October, November, December, everything through here got 2 rainy seasons over the course of a year. Just the edges only got 1 rainy season. So these ecosystems have evolved to accommodate the volume of moisture and the volume of energy that they get. And we find that in these areas where we have lifting, and because we have lifting, we have cloud, and cloud is just a mechanism to deliver energy, we're going to translate that energy into a lot of biomass, which is forest. So up here at the subpolar lows, we also have a lifting mechanism, which is generating cloud mass. It's not as warm, so the cloud's not going to be as large, but we're going to then transfer that energy back to the surface of the earth across terrestrial environments and generate more forests. So all the way across Europe and Asia and North America, we've got these fantastic forests. So we often don't think of places like northern Canada as having forests, or northern Asia as having forests, but the fantastically large conifer forests or softwood forests band across this part of our globe. In the southern hemisphere, it's our ocean hemisphere, our water hemisphere again. So these subpolar lows are generating moisture, but they're raining on water mass, not land mass. So we're not generating any forests down here. In converse, because this has all rained out, by the time it gets to 30 degrees latitude, and remember that 30 degrees is going to move with the sunlight back and forth, it also creates a band. We've got lots of hot air that is falling towards the surface of the earth and a lot of sunshine. So this is where our deserts are going to be found, is in and around 30 degrees. So north of 30 and south of 30, we're going to get our big deserts. So the Sahara Desert all the way through Oman, all the way up to Turkey, across Uzbekistan, Kazakhstan. We've got the Gobi Desert over here, across to North America on the other side. We have the Sonoran Desert in North America. In the southern hemisphere, our deserts are smaller. So we've got the Kalahari here. We've got a large central desert in Australia, and then in South America, we have the Atacama Desert. It's a high elevation desert there. All right, guys.